Dear friends, in this lecture, let us concentrate on significant figures and rules for rounding of a value. Usually, after calculation of a physical quantity, we will have some dilemma of writing the final answer, whether to express in terms of 2 digits or 3 digits or 4 digits. Such problem arises. In order to address such problem, this lecture has been made. Let us try to understand what are the significant figures. When we do a measurement, what do? We use an instrument. As an example, in this case, I have taken a string which is here, whose length is measured using a meter scale. This meter scale has the least count of 1 millimeter. I will tell you about the least count later. It is actually the least possible measurement that can be carried out using an instrument. So this is a meter scale which is graduated in millimeter. So marked number, this number represents 1 centimeter, this is representing 2 centimeter. In that sense, this is 6 centimeter and 7 centimeter is somewhere here. And when we keep the meter scale this way, when we try to measure the length of the string, we mentally divide the 1 millimeter division. Which division? Here. We divide this into 10 equal parts and guess the reading as 6.74 centimeter. Let us assume that we are guessing that it is 6.7 because the value is lying between 6.7 and 6.8 here. So that we sometimes take it as 6.74. Of course, some other measuring person may be taking it as 6.75 or 6.76 also. Just as a typical example, I am taking 6.74 centimeter here. In this case, 6 and 7 are very certain, but the fourth one is uncertain. Why? As I mentioned earlier, if 3 different persons measure the length of the same string, one may say that it is 6.74 centimeter, the other person may say that it is 6.75, the next person may think that it is 6.76 centimeter. That means this third digit in this number is uncertain. But everybody is sure that it is 6.7 something. Hence, we say that 6 and 7 are certain and reliable numbers, whereas 4 is uncertain. And all these 3 digits are known as the significant figures. So then how to define it? If you take one more example, if time period is 1.62 second for a pendulum, for example, where 1 and 6 are certain, and this third decimal, that means third digit in this number is again uncertain. However, all the 3 digits 1, 6, 2 are known as the significant digits. And these significant figures usually indicate the precision of an instrument. There are few rules for determining them. Let us first understand the rules which are governing in estimating the significant figures. One is that the change in system of unit does not change the number of significant digits. Let us take an example. In this example, length of an object may be 2.308 centimeter. Now it has 4 significant figures. 2, 3, 0, 8 are significant figures, are significant digits. We can write in other units also. 0.02308 meter, 23.08 millimeter, or 23080 micrometer. So 3 different units have been used in order to express the same length. In all the cases, same number, I mean 2, 3, 0, 8 are the significant figures. Then what about this 0 and 0 behind decimal point and after the decimal point? If these are the only 4 significant figures, and in this example 2, 3, 0, 8 are the significant figures, then what about this 0? Let us understand what are the rules to be used in order to consider these number of significant figures. All non-zero digits are significant. This is the second rule. The first rule is that change in system of unit does not change the number of significant figures. Second is all non-zero digits are significant. And if it comes to zeros, all zeros between two non-zero digits are significant, no matter where the decimal point is. The fourth one is that if the number is less than 1, the zeros on the right of decimal point but to the left of the first non-zero digit are not significant. Let us take an example so that you will understand better. In this number, 0.002308 are there. In fact, here 2308 are the significant figures. As indicated here, all non-zero digits are significant. Okay, 238 are non-zero digits. And all zeros between two non-zero digits are also significant, so that this zero is also significant. But if the number, this is actually a number which is having value less than 1. In this case, zeros on the right of the decimal point, that means these two underlined zeros, but to the left of the first non-zero digit. First non-zero digit is this one, 2. So these two zeros are insignificant. That is the point. Hence 2308 are the significant numbers in this example. Now let us take another example wherein the terminal or trailing zeros in a number without a decimal point are not significant again. To take an example here, 123 centimeter can be written as 120 meter can be written as 12300 centimeter, 123,000 millimeter. Reason is that 1 meter has 100 centimeter and of course it is equal to 1000 millimeter. So that's why this same number can be expressed in different units as mentioned here. So the trailing zeros means these are the trailing zeros, 00 here and 000 in this case. These are not significant. So that means what? Whatever may be the system of unit, number of significant figures is same. 1, 2, 3 in this case, 1, 2, 3 in this case, 1, 2, 3. So same number of significant digits arise in this case. The trailing zeros in a number with a decimal point are significant. This is important. Here, for example, 3.500 is taken. This trailing zeros 0 and 0 are taken beyond the decimal point. Therefore, these zeros are to be considered as significant. And in the other example, 0.06900, this 6900 are significant, but 0 behind the first non-zero digit, that is 6, is not significant. So this is how one has to understand the nature of significant figures. How to avoid confusion about trailing zeros? You take one more example. Length is given as 4.700 meter. As I mentioned in the previous slide, here since trailing zeros 0 and 0 are taken after the decimal point, they are to be considered as significant. However, if there is no decimal point, if it is only 4700, in this case these two zeros are not significant figures. This number will have only two significant figures, 4 and 7. Whereas in this case 4.700, all 4 are significant figures. So trailing zeros convey precision of the measurement. Therefore, they are significant. This is the reason why these two zeros are considered to be significant figures. And it is true even if 4.700 meter is expressed as 470.0 centimeter. So one should not think that this zero is not having the significance. That is also significant figure. And here these two zeros are significant. These two zeros are also significant in this case. That means when you change the system of unit, one should not change the total number of significant figures. The ambiguity, if arises, can be removed by expressing the values in terms of power of 10 also. For example, 4.700 meter can be expressed as 4.700 into 10 power 3. Reason is 100 centimeter makes 1 meter. Therefore, that 100 can be taken as 10 square centimeter in the place of a meter. Similarly, 1000 millimeter makes 1 meter. So that in terms of, in the place of this meter, we take 10 power 3 millimeter. So that you will have no ambiguity. 4.700. So 4 significant figures, 4 significant figures, 4 significant figures in all the 3 cases. Can we round off a value? Yes, it is possible to round off a physical round of a quantity or a round of the value of a physical quantity. Let us understand those rules. If the digit to be dropped is less than 5, the next digit preceding to be retained is left unchanged. Take an example so that you will understand better. In this 6.34, while rounding off to 2 significant figures, 4 must be dropped. See, if the digit to be dropped is less than 5, so now 4 is less than 5. If 4 has to be dropped and 3 must be retained here. So 3 must be retained as it is without changing, because this number 4 is smaller than 5. Similarly, if the digit to be dropped is more than 5, then the next digit, that is preceding one, to be retained is raised by 1. Take another example wherein 6.37, where 7 is greater than 5. If you want to drop this 7, then you have to raise 3 by 1. That means 3 must be written as 4 in this number, hence 6.4 will be obtained. If the digit to be dropped is 5 itself, then the next digit, that is the preceding one to be retained, is left unchanged if it is an even number. You just observe. In this case, 6.45. While rounding off to 2 significant figures, 5 must be dropped. Since 4 here is an even number, we can drop this 5 without changing 4. So that 6.4 is answered. However, if the number behind the third digit is an odd number, like 7 here in this case, in this example 6.75, if you want to drop 5 in this number, since 7 is an odd number, you have to raise it by 1, so that your answer will be 6.8. How to decide about number of significant figures in calculations? It all depends on the least count of the instrument as well as the mathematical operations used. What is the least count? As I mentioned earlier, it is the smallest quantity that can be measured using an instrument. Least count of a meter scale, for example, is 1 millimeter. It can also be mentioned as 0.1 centimeter. And for a slide calipers, if you have measured in your laboratory, you can understand that it is 0.01 centimeter. Whereas for a screw gauge, it is 0.001 centimeter. The degree of precision is actually determined in terms of the least count. Suppose the length is measured using a meter scale, which is 1.5 centimeter. It can have only one significant figure after the decimal point, as LC has one significant figure. So one should not express the value as 1.515354 centimeter, because the least count has only one significant figure after the decimal point for the meter scale. So totally 2 significant figures. Suppose the same length is measured using a slide calipers, whose least count is 0.01 centimeter. Therefore, the value that we measure can be expressed with 3 significant figures. That means only 2 significant figures after the decimal point, because least count of the slide calipers is 0.01 centimeter. It is having 2 significant figures after the decimal point. Therefore, you have to take 1.54 only. One should not write it as 1.543546 like that. Similarly, if the length of the instrument is measured using a screw gauge whose least count is 0.001 centimeter, in that case the value that you can express is only having 4 significant figures, I mean 3 significant figures after the decimal point. So 1.526 for example. In that case, in this way, one has to express the value based on the decimal points which have been significant figures which have been observed or found after the decimal point. Now let us recall the example which I had taken in my lecture 2, wherein the period of oscillation of a pendulum is successively measured. The values obtained were given this way and percentage of error was to be calculated. So there in that calculation I had shown that the percentage of error was 2%, and it was already told in that lecture that there is a chance to get answer 2.3% and 2.24% also if you do not round off the value using the rules that I described in the previous slides. In order to understand how to solve this problem, if one is interested, you can watch the lecture 2. The link of the same is provided in the description. Rules for arithmetic operations, because the significant figures will be decided based on the arithmetic operations also. In case you are adding or subtracting a certain number of values like 2.5, 1.54, 3.668, etc., you will get an answer of this kind, wherein the significant figures you are getting are 4 after the decimal point. But what should be my answer? You have to identify the least significant number in this calculation. 2.5 is having the least significant digits. Therefore, the final answer must have least significant digits after the decimal point is only 1. Therefore, you have to write only one significant figure after the decimal point. So, this is how to express the answer in the case of subtraction and addition. Whereas in the case of multiplication and division, if you divide a number by another number, you will get an answer having a number of significant figures, but the final answer must have total 3 significant figures only, because out of the values that you have taken for calculation, the number 10.3 is having the least significant digits. So that final answer must also be having the number of significant figures equal to the number having the least significant digits. And in the Karnataka CET, you can find this question wherein the vernier calipers, the vernier scale of a traveling microscope has 50 divisions which coincides with 49 main scale division. If each main scale division is 0.5 millimeter, then the least count of the microscope, how much is the least count of the microscope? That's the question. So the least count of a traveling microscope can be calculated using a relation given here, 1 minus number of divisions coinciding with total vernier scale division. In the data it is given to be 49 and total number of vernier scale division is 50. Therefore, and value of one main scale division, that is also given to be 0.5 millimeter. On substituting, you will get 0.01 millimeter. That is the answer for that question. And then in NEET 2023, you can find another question related to the errors. Errors in the measurement which arise due to unpredictable fluctuations in temperature and voltage supply are least count errors, random errors, instrumental errors, and personal errors. I had given the definitions of all these kind of errors in the previous lecture. If one has gone through that lecture, it is not a difficult task to understand the answer for this particular question, wherein answer is random error. So if you have not understood what would be the reason for selecting this answer, please watch second lecture, which is provided in the description in terms of the link.